Hey everyone, welcome back to another lecture, and today we're going to talk about lenses. And what you're going to see is that convex lenses form images like concave mirrors and vice versa, okay? So you're going to see some correlation between the images formed by mirrors and lenses, but the opposite will be true for concave mirrors and concave lenses. So in general, we know that lenses can magnify or shrink images, right? Because we use magnifying glasses to zoom in on stuff, and we use corrective contacts and eyeglasses to change the shape of the image that we see in order to fit our eye. So, right, lenses can magnify or shrink objects or images of objects, and depending on the location of the object in relation to the focal length, right? Same as with mirrors. And also depending on if this is a concave or a convex lens. So lenses are transparent materials, right? They don't reflect anything. They allow the light to go straight through. And so the law of refraction is what's going to be governing this property, right? This image formation. And we're going to take a look at that. So let's remind ourselves of the law of refraction, okay? Snell's law. When light enters one medium and goes into a slower medium, right? And a slower medium means a higher index of refraction. So when we go from a low index of refraction to a high index of refraction, the light slows down and it bends toward the normal. Okay? Now, when light enters one medium and goes into a faster one, that means we are going into a slower index of refraction, right? So, faster light travel means lower N. Let me write N. There we go. We move into a smaller index of refraction. The light's going to start moving faster, and what happens is it bends away from the normal, okay? And in our situations here, what we could say is that N1 is the incident media and N2 is the lens, okay? So it is possible, right, to have a lens in air, right? We're outside in air. Here's the lens. And the lens would have a higher index of refraction than air. But we could also take that very same lens. Let's say that its index of refraction is 1.5. And this is 1. And let's put that very same lens in water. Nope, not water. We're going to put it in like, I don't know, some kind of gas. And the reason why I didn't choose water is because water has an index of refraction of 1.33. So that's not going to help us out. Let's put it in some kind of gas where gas has a larger index of refraction than the lens. So let's say it has an index of 1.65. Okay, so we could very well put a lens in a medium that has a higher index of refraction, where we would get the light rays to bend away from the normal instead of bending toward the normal. Okay, so let's talk about now like the geometry of a lens. We're going to be dealing with curved lenses. So we're going to be having light rays moving parallel to each other. And when they enter a curved part of the lens where the curve is like this, so we would call that like a convex, what's going to happen is they're going to obey the law of refraction, and if N glass is greater than N air, they're going to bend inward, right? Well, what if they are traveling through the glass in parallel rays, and then they encounter this curved surface? So that would look like a concave surface. And they're going to exit into air, which has a lower index of refraction. What's going to happen? They're going to bend inward as well. Okay? And the opposite will be true if we were to flip the indices of refraction, right? Like in this case, what if the lens has a lower index of refraction than the air around it, then we would get the opposite to be true. And that's what's in the red text here. And so we can consider the opposite geometry. So what if now our parallel light rays are entering a lens that has a concave shape? Well, then what's going to happen is the light rays are going to bend away from the focal point, right? They're going to diverge. And if those light rays are starting off in an index that's higher, right, and they enter an index that's lower, well, if this is if it's meeting a shape, a convex shape, right, according to this light ray, this is a convex shape, and it's going to also bend away from the normal. And so flipping the signs of the indices of refraction from high to low and low to high will give you the opposite effect. So in general, we're going to have two types of lenses, okay, based on those effects. We're going to have a converging lens and a diverging lens. So a converging lens can have two convex surfaces, okay, and it can also have one convex surface and then one planar surface. And that's called a plano-convex lens. And it's going to converge the light. And when light parallel rays enter the lens and then exit the lens, they're going to all converge at the focal point. So this is true for both types of lenses, okay? And that's because the planar part doesn't diffract the light, doesn't change its direction, I should say, right? And so it just continues on its convergent path, as we saw up here, okay? So what about diverging lenses? So diverging lenses have two concave surfaces. It's called a concave lens. You can also have a plano-concave lens, okay? And what's going to happen is the light rays are going to diverge away from the principal axis. And if you trace those back, you see that it looks like they're coming from the focal point, right? If your eyes are here, seeing these light rays, they're going to trace it back and it's going to look like the light rays are coming from a focal point. And so take a look at this picture, right, and compare it to this one right here, right? The light rays are in that glass and they're exiting into air or into the outside material, and they're going to diverge outward. And so your eyes are going to trace these guys back to a focal point. Okay? So in general, because there's other types of lenses, they're called like meniscus lenses, and you can have slightly different, right? These have equal radius or radii of curvature, right? Equal radii of curvature. You can have other kinds that have unequal radii of curvature like that, like a moon shape, called meniscus lenses. And you can categorize them pretty easily by thinking about this general rule. So a lens that's thicker in the middle, right? Thick in the middle, he's going to be a converging lens. And a lens that's thinner in the middle, he's going to be a diverging lens, okay? So it doesn't matter if these are different radii of curvature. If it's thinner in the middle, it's diverging. If it's thicker in the middle, it's converging lens, all right? And so as the title of this section stated, right, the curvature of the lens has an opposite effect to that very same curvature in a mirror. Concave mirrors cause light rays to converge upon reflection, but concave lenses cause light rays to diverge. Convex mirrors cause light rays to diverge. Convex lenses cause light rays to converge. Okay, so opposites. Okay. We're going to make an assumption about these lenses, and it's the same assumption that we made with the mirrors, but I didn't really talk about it in the lecture. We're going to ignore any spherical aberration, which basically what a spherical aberration is, if this lens or mirror curvature was like around the same order of magnitude as the height of the lens or the mirror, Well, what would happen is the focal length would actually kind of like spread out. So like the light rays that reflect here would converge on a certain focal point, and the light rays that come from over here would be at a slightly different focal point. That's called spherical aberration. We're going to ignore that. And we can ignore that by assuming that the height of the lens or the mirror is small compared to that entire radius of curvature. So like, we had some radius of curvatures of like 18 centimeters, 20 centimeters. So that means like our lens or our mirror was like actually kind of small, like maybe 1 or 2 centimeters tall compared to that entire radius of curvature. So by doing that, we are going to ensure that the focal point, that like all the light that either refracts or reflects is going to just hit the very same focal point, okay? So there's nothing here you need to do here. This is just for your information. Okay, we're going to be talking about thin lenses, and basically we're only going to consider thin lenses for the rest of this chapter. We're going to neglect any effects of spherical aberration, okay? Eyeglasses and contact lenses, we have to use this approximation, or else everything we would see would be blurry and it would defeat the purpose. Okay, so let's look at some ray diagrams. Let's start with converging lenses, and let's put our object outside of the focal point, okay? So our object is outside of the focal point, and let's kind of like get the landscape. What are we doing with the lens? When I use a lens, what am I doing? Where am I putting my object? I am putting it on the opposite side of the lens than me, right? So it doesn't make any, so where's my eye here? My eye is receiving these arrows, okay, pointing straight into my eye. My eye is receiving these arrows. My eye is over here, okay? And I'm putting my object on the other side of the lens. Why? Because why would I put it here, right? If I'm using the lens to help me see that object better. If I put it in front of the lens, well, I'm looking at the object as it is, right? Why would I put it there? I'm putting the object on the other side of the lens than my eye, okay? Here's my eye. The object goes on this side, okay? And why am I making such a big deal? Because for mirrors, we put the object on the same side, don't we, right? Because if we put the object behind the mirror, we can't see it. The mirror's blocking it. So this is an important step in understanding the images formed by lenses, okay? Our eye is over here now, and we want to see the image produced by this lens when we put the object on the other side of the lens. And here's why. So light rays are going to, come from some source, okay? And they're going to bounce off the object, and they're going to go through the lens toward our eye. And then we have those 3 principal rays that we use to construct our ray diagram. And here they are. And what you're going to see is that now, instead of reflecting back like they did for mirrors, they're going to refract, okay? And wherever they refract is going to, and where they converge at that point, is going to form the image. And so what you can see is, for a converging lens, where the object is outside the focal point, okay, here's the focal point. There's 2 focal points, by the way, right? One for this side and one for this side. And we'll get into that coming up. And so if we place that object outside the focal point, and so what kind of image do we see? We see an image that is shrunken, that is inverted, and on the other side of the lens than the object. Its location is also going to be outside of the focal point. Okay, so these are the characteristics of an image created by a converging lens, where we've placed that object outside of the focal point. So to construct this ray diagram, we use the 3 principal rays, and here is a description of them in terms of lenses. So the first principal ray arrives at the lens, and it travels parallel to the principal axis, okay? And then where it's going to refract is through the focal point. The second ray enters the lens directly through the center, and it keeps going in a straight line. The third principal ray goes through the focal point on the left side of the lens and then hits the lens and travels in a straight line. So it's kind of like the opposite of this one. You see that? They're opposites. And so where those three guys meet is going to be the head of the image of the object. Okay? So those are the three principal rays. And what that produces is an inverted object that looks smaller, right? And it looks like it's on the other side of the lens. Okay? In other words, it looks like it's closer to us than the object, right? Because where are we? We're over here, right? We're over here on this side, right? We're on this side. The object, the pyramids are all the way over there. And this image looks like it's closer to us, okay? It looks like it's on our side of the lens. So a real image formed by a lens is on the side of the lens opposite to the object, right? We've defined a real image in terms of mirrors as one that forms where the reflected rays converge. Well, we're going to use the same description here, right? Where the actual rays are converging, not the dashed ones, but the solid ones, right? Where the actual rays are converging, we call that the real side, right? It's made by real rays. We didn't have to use our virtual, dashed rays to create that convergence point here, right? We were able to use the real rays. We didn't have to trace anything back. So this image that's created is a real image, okay? It's a real image. And we define the real image as one that forms where either the reflected or refracted rays converge, not the ones that we traced back. Those would be virtual. So just to compare between mirrors and lenses, right? Concave mirror causes light rays to converge only on the reflective side of the mirror, which is where we would put the object, right? So that's the only side that a real image can form. However, for a lens, it only causes light rays to converge on the side of the lens opposite to the object. So the real side for lenses is not on the side of the object anymore, right? Like it was for mirrors. The real side of a lens is on the side opposite to the object. And that's because that's where the light rays go and where the real rays would converge to form an image. And if we had to trace them back and, do kind of like, where does our eye think it's coming from? If we had to trace it back to find where they converge, then that would be a virtual image, okay? And we'll look at an example of that. So the only time where a converging lens can produce a real image is if the object is outside the focal point. So now, let's place the object inside the focal point, okay? So here's the focal point. Here's our object. Our eye's over here, okay? We're going to draw those principal rays. We're only going to draw 2 of them this time. And that's because the third one is supposed to go through this focal point, but that's like in the opposite direction of where our eye is, so we don't really care where that is. So we only need the 2. And what you see is that when they pass through the lens, they diverge from each other, right? They're never going to converge over here. They're spreading apart, right? They're getting farther and farther apart from each other. And so what we need to do is our eye's over here, looking at it. How did I draw the eye? The eye was like this. Okay, I lost my mind for a minute. There's my eye, right? He's like, oh, where did these rays come from? Well, we're going to trace it back, and where they converge, okay, is where the image will be. And guess what? The image, it's on the same side of the object. And for lenses, when the image is on the same side of the object, it's a virtual image, right, of the object. And the second reason why it's a virtual image is because we had to trace those lines back, Okay, our eye had to produce that image virtually by assuming the light rays came from straight back, not from here and here, right? Our eyes don't know any better. Our eyes think that that light ray came from straight back because it doesn't know about the law of refraction. It doesn't know about that. So that image is now going to be behind the object, and it's going to be big, all right? And it's going to be virtual, okay? So it's going to be magnified, virtual, and upright, okay? So, and that's for any object placed within the focal point of the lens, okay? So this text, right, we didn't draw that third ray because it's over here and it points away from our eye, right? So we don't care. And where those light rays meet is the location, right? Or we have to trace it back. Where they meet is the location of the image. And because the light rays do not actually cross there, right? We had to kind of pretend that they do. It's a virtual image. And since that since that image is on the same side of the lens as the object, it's virtual, and therefore its image distance is negative, right? Just how we defined it for mirrors. If it was virtual, then the distance was negative, right? But now it's just located on a different side. So what about diverging lenses? Okay, so we have a lot less cases now than with mirrors, which is great. So we have 2 cases for converging lenses, 1 case for diverging lens. So a ray diagram of a diverging lens looks like this. We're going to place our object outside the focal point, okay? And the lens is going to cause parallel light rays to diverge on the other side. And we can see that when we draw our principal rays, that we are going to get divergence of the rays on the right, on the outgoing side. And so our eye that's over here is going to have to trace back these rays, to see where they converge and put the image and place the image. So the image from a diverging lens is going to be virtual, right? Because it's on the same side as the object. And it's shrunken, okay? And it's upright. So these are the properties of an image created by a diverging lens where the object is placed outside of the focal point. So this got the concept. It's a little bit tricky. I kind of like wrote the answer out here and I drew a diagram. Okay, so I want you to, let's look at it, and I want you to think about kind of the first few slides we talked about. So let's say we make a lens with 2 convex surfaces, okay? 2 convex surfaces, what's that? That looks like this, right? And so you might think in your head, oh, we're gonna have a converging lens, okay? So it's 2 convex surfaces. Its index of the lens is 1.3. But now we're gonna place it in sugar water, which has an index that is higher, okay? And if we place the object that we're going to look at with the lens in the tank in front of the lens, and what kind of image is it? So is it a real image? Is it a virtual image that's larger, or is it a virtual image that's smaller? And I already kind of wrote the answer there, okay? And so here's the idea of why that's the answer. It says virtual image is smaller than the object. Well, hold on. You go up here to converging lenses, and that's not at all a possibility for converging lenses, right? Converging lenses either make a virtual image that's larger or a real image that's smaller. So how is part C the answer? Well, you may notice that if part C is the answer, we're just kind of playing with logic here, okay? If part C is the answer, part C is a virtual image that's smaller than the object. Well, that's a diverging lens. I'm so confused, right? Well, guess what? We kind of have swapped the indices of refraction from the typical, right? The indices of refraction are typically outside is less than the lens, right? We're in air and we're going through glass. But now we've swapped that. And so the concept here is that when the index of refraction of the lens is less than the outside area, you're going to get the opposite type of lens. So instead of having a converging lens, those two convex surfaces are now going to be a diverging lens. Okay, and diverging lenses always make virtual and smaller objects. So here's a schematic of what's happening. And this is related, these ray diagrams is related to these first few slides all the way up here. Let me just show you, right? Right, these two right here. This guy, well, we're going from a slower to a faster. So this guy, okay, right, this situation here, and this situation here, okay? We're going to turn that into a diverging lens. We're going to turn that convex lens, that's typically a converging lens, into a diverging lens by placing it in a medium with a higher index of refraction. And so here's the two situations. This is what we're used to, right? Because we use lenses in air, right? We put glasses on in air, right? But in this got the concept, we have placed the lens in some water that has a higher index of refraction. And so now those rays are going to bend away from the normal, right? Because as they go into a slower medium, they're going to bend away from the normal. Okay. So that's got the concept here. Okay. So to wrap up, we qualitatively looked at what converging and diverging lenses do in the eyes of the law of refraction. We compared the indices of refraction of the outside medium and the lens, right? So in general, when parallel rays enter one side of a convex lens, they exit the lens converging toward the focal point. Okay, so that's why convex lenses are converging lenses. And this is when the index, right, of the outside is less than the index of the lens. When parallel light rays enter a concave lens, let me draw it, right? There's convex, here's concave, right? Like this. A concave lens, a diverging lens, they exit diverging away from the focal point that's on that side. But the opposite can be true. So this is only true for N1 less than N2, but the opposite can be true if that lens happens to have a smaller index than the surrounding material, okay? As we saw in the Got the Concept. And so, but for all of these as we're talking about N1 less than N2, right? The air is 1, index of refraction of 1, and then the glass or the lens is something bigger than that. So when we're talking about that context, a convex lens always produces a real image if the object is outside the focal point. A convex lens always produces a virtual image if the object is inside the focal point. And then for a concave lens, it always produces a virtual image no matter what. Okay? Let's talk, before we do some math, like how we did with the mirrors, right? We had a mirror equation, and we had the magnification equation. Let's talk about one more aspect of lenses, and then we'll get into using equations like the mirror equation, okay? And that aspect is calculating the focal length of a lens. The focal length of a lens is determined by the index of refraction of what it's made of and the curvature of its surfaces. So the focal length of a thin lens, it depends on index of refraction and the curvature, right? And that's because the greater the value of n, the more sharply the light ray will be bent, right? Because if it's going into a medium with a very big difference in index of refraction, it's going to bend more, okay? So the focal length depends on that. It also depends on the shape, as we saw in the second set of slides in the beginning of this lecture here. And we can put these two pieces of information together into a mathematical expression, which we call the Lensmaker's equation. And so this is the Lensmaker's equation. So inverse of the focal length of a lens is determined by the index of refraction of that lens, minus 1, times 1 over R1 minus 1 over R2. So don't worry about the derivation, okay? As usual, we skip that. So we just need to know how to use these equations properly. And so the radius of curvature of lens 1 is the surface that's closest to the object. Okay, so the side subscript 1 is going to be, okay, if this is our lens and our object is here, this is going to be R1, the radius of curvature of this guy. Okay? This is going to be R2. Okay? So the value of the radii of curvature depends on, how sharply and in what direction those two surfaces are curved. So in this picture here, we can see that we have a converging lens, right? A convex lens. And what do we know about the radius of curvature? It basically is the center of the sphere that creates that curvature, right? So for convex lenses, this can be a little bit confusing. And here's why. Because R1, so this is the side of R1, right? But where's the center of that sphere? It's over here on the right-hand side, isn't it? Right? If I make this sphere, it's over here on the right-hand side. So R1 is going to have a positive radius of curvature because its center of curvature is on the other side of the lens from the object. Okay? R1 is this surface, right? But when we trace the sphere that creates that shape, its center happens to be on the opposite side. And so we're going to denote that as positive. Okay? Now, R2 is this guy right here. Let me draw a different color, right? R2 is this guy. But where's his center? Well, let's trace the sphere out. His center is over here. And if his center is on the same side of the object, then it's going to be considered negative. Okay, so there's a new sign rule in town. Okay, so this new sign rule states that if R1, if the center of curvature that creates R1 is on the side of the opposite side of the object, then it's positive. And if the center of curvature that creates R is on the same side as the object, then it's negative. Okay? And there's going to be a whole table that summarizes that to remind you. So, as R changes, so let me write the equation again, right? It was 1 over F equals N minus 1 over R1 minus 1 over R2, right? So as R increases, well then 1 over F is going to decrease, which means F increases, right? So if R, let me write this a little bit more straightforward. If R gets bigger, F gets bigger, right? They're both inverse from each other. I mean, they're not inverted from each other, right? They're both in the denominator. So they're going to go up. They're not going to have an inverse relationship, right? So if R increases, F increases. If R decreases, F decreases. Do we agree with that? And so that's what this paragraph says right here, right? The more tightly curved the surface, right, the smaller the R. then the smaller the f. Okay? And vice versa. So it's common to characterize 1 over f, so that we're not talking about like an inverted, parameter, as the power or of the lens or the mirror. Okay? So the units of power are diopters, which is simply an inverse meter. Okay, so if we wanted to find the power of the lens, well, we would just kind of like figure all this out, and we wouldn't invert it to solve for f. We would just calculate the right-hand side, and that would be the power. Okay, and we'll do an example about that. So the larger the power, so now let's, like, why did we do this? Why are we calling 1 over f power? Well, here's why. Because then this makes sense. The larger the power of a lens, the greater amount of refraction it causes, right? The more bent, the more powerfully it causes light to bend. Okay, let's look at a picture. Let's draw a picture. Okay, let's say we have a lens here, and then we have another lens here. And this lens has a focal length of 2f, and this lens has a focal length of f. Okay? Look how much more the light is bent, right? It's bent more because this f is smaller than 2f, isn't it? Right? So bent more. So if f is smaller, the light is bending more. And if f is smaller, the power is higher, because power and focal length are inversely related, right? So f is small makes the power big because it bends the light more. Okay? If parallel light rays enter a thin convex lens of power 2 diopters, then it comes to a focus at 0.5 meter behind the lens, because 2 equals 2 equals 1 over 0.5. Right? 1 over 1/2. You agree with that? Right? That brings the 2 upstairs. And if light rays enter a 5 diopter converging lens, then f is 1/5, right? Which is smaller than 1/2. In other words, 0.2. So the light would converge at 0.2. Okay? So larger power, smaller power. Okay? So, concave lenses, they have 2 focal points, right? One on the left and one on the right. So there's a negative focal length and a positive focal length. And the side depends on the sign rules that we apply, right? If it's on the same side of the object, then it's negative. And if it's on the opposite side of the object, if that focal point's on the opposite side, then it's positive. Okay? So that's how you determine the sign rules of the focal length. So now that we've kind of looked at some sign rules for focal length, let's quote, derive, unquote, the image position equation and the magnification equation for lenses. Okay, it's done through geometry in a very similar way as the mirrors, and I'm going to cut to the chase here. The equation is exactly the same for mirrors and lenses, right? It's exactly the same. The only difference is that you're going to have a different set of sign rules for lenses. Okay? So the image object distance relationship is the same for lenses and mirrors, but we have different sign rules that we apply. The magnification equation is exactly the same, okay? Except we have different sign rules that we apply for DI and DL. HI and HO have the same sign rules. If it's upright, it's positive. If it's inverted, it's negative. So the H's have the same sign rules. The distances have opposite, and that's all in a table. So we'll see it, okay? Here it is. So this is for lenses specifically, and then there's table 24.1, that's for mirrors, okay? And you can kind of put them next to each other, and I think there might even be in the book, like in the summary, like a table that has them both together. Check that out. But here's the sign conventions for lenses. Let's kind of go over it real quick, right? The radius of curvature and is going to be positive if the center of curvature is on the side opposite to the to the object. And it's going to be negative if the center of curvature is on the same side. And the focal length is going to be positive for a converging lens and negative for a diverging lens. Okay? And the image distance, this is where things get flipped from mirrors. It's now going to be positive if the image is on the opposite side of the lens as the object is. And then that's what we call real for lenses. The image distance is going to be negative if it's on the same side as the object, right? And that's where it's opposite from mirrors. And then we call that a virtual image. Image height, same. Okay, as mirrors. And the upright or inverted, same. Okay. So because the equations for mirrors and lenses are the same, right, we can draw many conclusions about the image. Okay. If a lens has a positive focal length and it's converging, and an object is placed outside of the focal point, then the image is real and inverted. So the solving basically these two equations is what tells us that, okay? And depending on the object distance, though, the image can be smaller or larger or the same size as the object. Now, if we place an object in front of a converging lens and we place it inside the focal point. This one was outside. Now we're placing it inside the focal point, right? It's real close to the lens. Then the image produces virtual upright and it's magnified. And that's the purpose of a magnifying glass. Right? We hold that glass like right up to our eye and we hold it right up to that object we want to magnify. We don't hold it really far away, do we? No. We bring it real close. We bring it inside the focal point so that it magnifies the image. And so it's upright, right? So we're not looking at an upside down image. So finally, for diverging lenses, okay, the image is virtual, the image is upright, and it's always smaller than the object. And this is true for any object distance. So we got two cases for converging lens, one case for diverging lens. Okay? Whereas for mirrors, concave mirrors, we had like 5 cases, didn't we? Right? And diverging, we had 2. So a key difference, just to reiterate again, the key difference between mirrors and lenses is the position of the image. Where is the image located, right? For a mirror, a real image is on the same side as the object, and a virtual is on the opposite. But for a lens, a real image is on the opposite side of the lens from the object, and a virtual image is on the same side of the lens as the object. Okay, so it's very important to understand the differences there. And that's where the sign convention difference is, right? With DI. So let's do some examples. We're going to do a bunch of examples in a row, okay, using the lens maker's equation, and then using the last example, we'll be using the lens equation / mirror equation, okay? So this is for lens makers because we're going to be calculating a focal length. So if you're calculating a focal length, you are using the lens makers, okay? So in figure 2434, I'll pull that figure up. Surface 1 of the lens has a radius of curvature of 15, and then the back surface, surface 2, has a radius of curvature of 25, and the lens is made of crown glass, index of refraction of 1.52. So figure 2434 is this. Oh, did I put it in here? I think it's, no, did I not put it in here? Oh, it's this one right here that I drew all over. This one right here. Let me pull it and put it into the picture. So we're talking about this picture right here. We want to calculate the focal length of the lens. So we're going to use the lens maker's equation. Okay, which is 1 over f equals n minus 1, 1 over r1 minus 1 over r2. So the tricky part here is assigning the correct signs for r1 and r2. Okay, so r1 is the side closest to the object. And since we're dealing with a convex lens, when we trace our sphere, okay, it's kind of like an egg shape, but use your imagination. It's spherical as much as possible. When we trace that out, what we see is that the center of curvature is here on the opposite side of the lens than the object is. And so we're going to give that a positive value, okay? So R1 is going to be positive, and that value was 15. R2, so it's a convex lens, so here's R2, and when we trace out our circle, we see that its center of curvature is on the same side as the object, so R2 is going to be negative, and R2 will be negative 25 centimeters. And then we were given the index of refraction as 1.52, so we can simply plug everything in with our signs correct. Right, so minus minus, give us a plus. So we're going to get 1 over f as 0.52 times 1 over 15 plus 1 over 25. That comes out to 0.1067. Multiply that by 0.52. We get 0.055 centimeter inverse. And if we want to turn that into a focal length, we need to find the inverse of that. And that's 18.1 centimeters roughly. Okay? And the power then, the power is units of meters inverse. So if we wanted to find the power of this lens, we would need to convert this to meters. Okay? So to convert that to meters inverse, okay, let me write this as 1 over cm. So I'm going to get rid of the cm's and put a meter. So how many centimeters are in a meter? 100 cm's are in 1 meter. So we're going to multiply that by 100. And we get a power of 5.5. Okay? So part B. Now we're going to flip the orientation of the lens so that the front surface has a magnitude 25, the back surface has magnitude 15, and calculate the focal length in this case. So we're going to have this same picture. Didn't leave us enough room. See if I can scoot this up a little bit. Okay. So I want to draw the picture because I feel like that's going to be important. So here's our 2 radii of curvatures. Okay. Now this is going to be, this is R1 which now has magnitude 25. This is R2, which now has magnitude 15. Okay, so what sign is R1 going to be? So we trace our little sphere. We see that it's located on the opposite side than the object. So R1 is going to be greater than 0, and R1 is then going to be positive 25. And R2, we trace our little circle out, and here he's on the same side as the object, so R2 will be negative, and R2 then will be negative 15. So let's solve our for our focal length again. So 1.520 minus 1. So now we're going to have R1 minus R2. So we're going to have 1 over 25 minus a negative 1 over 15, which is the same as this, isn't it? Right? It's 1 over 15 plus 1 over 25. So we're going to get the exact same focal length, aren't we? Get the exact same. So you can flip this lens, okay? Pick it up, flip it over, and it's going to have the same properties. The image formed is going to have the exact same properties, okay? So a focal length stays the same after we flip it back to front, okay? And the focal length is positive, isn't it? Okay, it's positive, which is what we saw in our, because it's a converging lens, right? It came out to be positive, which makes sense in terms of our sine rules. And it doesn't matter which way you flip it, it's still going to be a converging lens, okay? So, and then the power was 5.55 diopters. So now let's do the same thing for a a diverging lens, a concave lens, okay? It's made of crown glass, and it has a concave front and back. And the front surface has a radius of curvature of 15, and the back surface has a radius of curvature of 25. So here's a picture of it, okay? And so it shows us the signs already, but let's kind of verify that. So remember, R1 is this side right here, and now it's concave, so its center is going to be on the same side as the object. And so that makes it negative, doesn't it? And here's our second surface, and its center happens to be on the opposite side, so it's going to be positive, okay? And if that gets confusing, look at your sine rules and make sure you're drawing, right? R1 is defined as the surface that is first, right? Closest to the object. So if we trace that sphere out and its center happens to be on the same side as the object, then that value will be negative. So we're going to use the lens maker's equation. And so R1 is now negative. R2 is positive. And there's always a minus sign in the lens makers, right? They're both minus signs. And so now you're going to see definitely going to get a negative number, aren't we? Right? Negative 1 over 15 minus 25. That's going to give us a negative F, which makes sense because remember we saw that diverging lenses have negative focal lengths or focal points. So let's go ahead. Oh, why did I do that? I forgot my minus 1 here, didn't I? There we go. So we're going to get 0.520 times negative 1 over 15 minus 1 over 25. And that is negative 0.1067. And that's going to give us a 1 over F as negative 0.055 like we had before. And so our focal length will now be negative 18.1. And our power will be negative 5.55 diopters. Okay, using the same mathematical steps we did before, except now we just have a negative sign in front. because diverging lenses have negative focal lengths. Okay? So for the last example, let's look at the properties of an image made by a convex lens. So if we're examining the properties of an image, or if we're given the properties of the image and the object distance, then we know we're going to be using the mirror/lens equation, which is 1 over f equals 1 over di plus 1 over do. And the magnification is hi over ho equals negative di over do. Okay? So we have a thin convex lens, and it has a focal length of 15. So first question is, f is 15. Magnitude of f is 15. Is it positive or negative? Well, it's a convex lens, and convex lenses are converging lenses, okay? So we know that it's going to be a positive value. So f is going to be equal to positive 15. How far from the lens does the image form? So what is di? When an object is placed 9 centimeters from the center of the lens. So do is 9 centimeters. Is the image real or virtual? And is the image inverted or upright? And by what factor is the image magnified? Okay, so 1 over f equals 1 over di plus 1 over do. So let's solve for di. 1 over f minus 1 over do will give me 1 over di. So 1 over f is 1 over 15 because it's positive, minus my object distance is always positive. And then di will be, so I'm going to do 1 over 15 minus 1 over 9. And I'm going to get a negative number. What I get is 1 over di is negative 0.04 repeating. If I convert that to centimeters, right, I'm going to do inverse of that. And I'm going to get negative 22.5 centimeters. So my image value, my image distance is negative. What does that mean for lenses, right? It means that it's a virtual image, doesn't it? And if that image is virtual, where is it? It means it's on the same side of the lens as the object. And so let's write that down, and let's go get a picture, right? So it's image, so let's do do is negative 22.5, di is negative 22.5 centimeters, okay? Virtual, by virtue of its negativity. And so it's a converging lens, right? And we placed the object within the focal point, didn't we? So let's go pull the ray diagram for that situation. That was way up here. I'm going to scroll fast. There it was. Just past it. Right? And certainly we're going to get this, aren't we? Let's pull this whole thing down there. One more. There we go. Okay. So let's kind of like check everything. Okay, so what we got is an image distance that is 22 centimeters, 22.5 centimeters away from the lens. Okay, so, and it's negative, so that's this guy right here. That checks out, right? Our object was placed within the focal point. That checks out. And is the image upright or inverted. Well, according to this picture, it's upright, but let's verify that with the math. So to verify its uprightness, we are going to relate the image height. Well, I guess we're going to need to find the image height, don't we? We're going to find the magnification. Let's just write this down. HI over HO negative DI over DO. Well, we have DI and DO. We don't know the H's, do we? We don't know anything about the height. So we don't need to in order to know if it's upright or not. Because if the magnification is positive, we know that the object is going to be, or the image is going to point in the same direction as the object, okay? So we know what's DI over DO. DI is negative 22.5 centimeters over DO, which is 9 centimeters. And so what we get of our magnification, we're going to get a positive magnification, okay, of 2.5. So because the magnification is positive, we know that the image is upright, or it's in the same, pointing in the very same direction as the object. So image is upright. We also know that by looking at the ray diagram, right? Image is upright. But now we've confirmed it with the math. And we also can see that the image is going to be bigger than the object, and it's going to be 2.5 times bigger. Okay? So to answer all the questions, the image is virtual, and it's upright, and it's magnified by 2.5. And its distance is 22.5 centimeters from the lens on the same side of the lens as the object. Okay, so when you're doing some problems like this, try to look back at like an already completed ray diagram. Look at the cases, right? We covered all the cases possible. So you don't have to redraw it every single time. You can just find the correct case and take a look at that ray diagram, okay? And the cases were defined by the object's distance in relation to the focal point. So this final got the concept. I just realized that the title of this, I might get confusing. The title of this is not a lens in sugar water. So we are not dealing with the situation where the outside of the lens is a higher index than the lens itself. Okay, the title of this got the concept is actually called lateral magnification. So we're finding the lateral magnification of a converging lens with different object distances. Okay, so there was a typo here in the slides. Okay, so let's think about it. So we have a converging lens, and its focal length is f. We're placing an object at each of the following distances listed here. And we're going to rank the images that are produced in order of their lateral magnification. So we're going to start with the most positive to the most negative. Okay? So we're given the focal length, and we're given the object distance. So we need to find the magnification. And the magnification is given in terms of the object and image distance as this. So what we're going to do is we're going to find the image distance and then plug that into the magnification equation. Okay, but it's all going to be algebraic. So for part A, I'm going to do part A and B, and then I'll let you guys do C, D, and E so that this lecture video is not, really long. So we're going to do 1 over F, and then I'm going to solve for DI, right? 1 over F minus 1 over DO is going to give us 1 over DI, right? So our focal length is F. Our DO for part A is 3F. And that's going to make our DI what? Well, let's multiply this by 3 over 3. It's going to be 3 minus 1 over 3F, which is 2 over 3F. That's our 1 over DI. So DI is going to be equal to 3F over 2. Okay? So now let's plug that into the magnification equation, which is negative DI over DO. So we get negative 3f over 2 divided by DO, which is like multiplying by 1 over DO, where DO is 3f. So we're going to see the 3f's cancel, and our magnification is going to be negative 1/2. Okay, so I want you to do that for parts B through E. And you can pause the video and do it. And then when you come back, I'll have the answers written down for you to check, okay? So here are the answers for the following. Okay, so here's all the magnifications, and if we're going to rank them from largest positive to most negative, well then it's going to be ranked as D, E, A, B, and then C. Okay, so to wrap up this section, the last section in this lecture, we're just talking about lenses today, is we were able to calculate, the focal length of a lens by looking at its index of refraction of the material and the radii of curvature. These radii can be positive or negative depending on the sign rules, okay, depending on where that center of curvature is located, all right? And then the more sharply the surface is curved of a lens, the smaller the f, okay? And the more powerful it is, because the power is related to inverse of the focal length, okay? And then the focal length is proportional to the radius of curvature. We use the mirror equation to find the image, location, and characteristics for lenses. So it's really the lens mirror equation, right? We use the same ones for magnification and for object and image distances. But we had different sign rules, right? There's a whole nother table for lenses. So the sign rules are slightly different. And that has to do with how we define a virtual image and a real image in lenses. So a virtual image for a lens means that image is located on the same side as the object. And a real image for a lens means that image is located on the other side of the lens than the object, okay? So go over those lens rules, do lots of practice for mirrors and lenses, and get comfortable with finding the image location and the characteristics of the image produced by mirrors and lenses. All right, and that's all for today. Have a great one.